Hi and welcome back. So over the past couple of videos, we've been working on solving this first order transient circuit problem with a resistor and a capacitor. And the past couple of videos, we did nodal analysis, got our differential equation, and the last video, we figured out the homogeneous part of our differential equation. So we figured out pretty much if we set this differential equation, if we set up this differential equation, set this relationship equal to 0, we found our VOH. We found the V out that satisfies this relationship, that's going to make this differential equation equal to 0. We found out that that was some constant k that we don't know yet times e raised to the minus t over RC. So now what we have to do in this video, what we're going to do in this video, is we're going to find our particular solution. It's called VOP, and it can be a function of time. And pretty much what that solution is going to do is kind of the same way in the last video we dealt with 0 is equal to RC times dV0 dt by V0. In this video, our VOP, our V out particular, is going to be the VO that satisfies this relationship, that satisfies VI is equal to RC times dV0 dt plus V0. And now we're going to call this VOP because that's what we're solving for. We're solving for our particular solution. One thing I want to say is if this is kind of confusing to you about having a homogeneous solution and a particular solution, I know I mentioned it earlier, but it would be a really good idea to check out the Khan Academy playlist, the Khan Academy's resources on differential equations, because Sal goes over solving differential equations in much more detail than I'm going to do, and does a better job going over how to solve all this stuff than I'm going to do here. But anyway, pretty much what we have to do, we already got our V out homogeneous. So now we have to get our V out particular. And the nice thing about getting our V out particular, let me actually, here, I'm just going to erase this real quick because I'm not going to need a lot of space to solve this. The nice thing about getting our V out particular, and typically what you're going to do for at least most of the techniques when you solve differential equations, when you need to solve for a particular solution, let me just go ahead and rewrite this here. Use a better color. VI is equal to RC times VOP dt plus VOP. So a couple of things I want to say about this. The first thing is we only need one function. We only need one thing. We only need to find one thing that we have to set VOP equal to. VOP is going to be set equal to one thing such that it satisfies this relationship. We only have to find one thing for our particular solution, one function that satisfies this relationship, and then that's going to be valid. That's going to be a valid particular solution for this differential equation. So that's the first thing. The second thing I want to say about this is the way you solve for a particular solution is basically guessing. Particularly when your input solution, when your VI gets to be a complicated equation, there are specific ways that you guess, and even there might be, when VI gets to be very complicated, and we are going to do problems like that, you actually solve the differential equation in a completely different way. But for the way we're going to do it right now, we're just going to essentially guess at an equation, right? Because we just have to find one thing. We just have to find one function that satisfies this equation. And now let me just show you what I guess our first guess is always going to be. The first guess that you're always pretty much going to make when you do this. And And if you are taking a differential equations class, they'll teach you better ways of guessing. And on the Khan Academy differential equations playlist, they teach you much more stuff about how to correctly guess your particular solution. But where I'm going to start here is, what if we said our V out particular was just equal to VI? What if we just said, okay, we're going to substitute in for VOP, we're just going to say that that was equal to VI. And keep in mind, VI, for what we're doing right now, VI is just a constant. It's like we had 5 volts, like a 5-volt source input on our circuit. So now, if we say that VOP is just equal to VI, let me just go ahead and make that substitution into this equation up here. So we have got VI is going to be equal to RC times d by dt of VI, because we would have VOP up here, but we're replacing it with VI. And then we're going to add on just VOP, but we're replacing VOP with VI. So I add on VI. So now, pretty much VI is equal to VI. So that's pretty straightforward over here, that we now just have the constant VI over here. But now we have RC times the derivative of VI. And keep in mind, for this equation right here, for these types of problems that we're going to do, VI is just a constant. It's like we add a 5-volt constant source. That's the way that's pretty much what you're going to have for these equations. So what is the derivative with respect to time of a constant? And hopefully you remember that it's just 0. So everything over here, VI, is just going to be equal to, everything here is just going to evaluate to 0 plus VI. So we have VI is equal to VI. So that means that this relationship checks out, and we now know our particular solution. Our V out particular is just going to be equal to VI, just the constant VI. So now we've got our particular solution. We've got our particular solution, and we've got our homogeneous solution. The last thing we have to do is just figure out what that constant K is. So now let me just say real quick, if you were taking a differential equations course, and there are times that circuits is going to feel a lot like a differential equations course. There's kind of from this point on out, there's going to be a lot of differential equations. But you learn kind of better ways to deal with solving the differential equations than we're going through right now. But if you were taking a differential equations course, what we have right now, what we have solved for so far, this is called the general form. The general form of the differential equation. And it's called that because we have not solved for the constant K yet. So the way we're going to solve for the constant K, and if you remember your differential equations course, if you had solved a differential equation, the way you would solve for that constant is by using what are called your initial conditions. So if you remember, I didn't necessarily give you any initial conditions for this problem. It wasn't like I expressly said, oh, well, our V out at time is equal to 0 is 5 volts, or is V out at time is equal to 12 is 10 volts. It wasn't like I told you any information like that. So really, what you're going to have to do to get those initial conditions in order to solve this is you're going to have to go back to the original circuit. So let me actually what I'm going to do is I'm going to just redraw. Let me move over here. Just get a nice clean slate. So write down what we've figured out so far. So we've figured out V out as a function of time is going to be equal to our particular solution, which we figured out was just VI, was just our input voltage, plus some constant K times e to the minus t over rc. And just to make sure, r and c are known values. We know what both r and c are right now. That's what your resistance value is. That's what your capacitance value is. And the last thing we should also say is that this solution is valid for all time greater than 0. That's what we're finding here. Before time is equal to 0, we don't necessarily know what the solution is, even though we're actually about to find that out, I guess. So this is what we figured out so far. This is the equation we have. V out as a function of time is equal to our particular solution, Vi, plus some constant k times e raised to the minus t divided by Rc. So now let me just go ahead. I'm going to redraw the original circuit. So we had our switch here, our resistor, and our capacitor, and we had ground right here. And at time is equal to 0, our switch closed, and this is our V out. This was the V out that we were looking for as a function of time. So now, if you remember at the beginning of the video, I said that the circuit was in the configuration with the switch open. Let me actually, here, I'm going to erase the arrow right now. The circuit was in this configuration with the switch open for a really long time. Any charge that was on the capacitor, and we're also going to say, like, before we built this circuit, we completely discharged the capacitor. We made sure that there wasn't any voltage across the capacitor before we started doing anything. We touched a wire to either side of the capacitor to discharge it completely. And then we built this circuit, and we left it in this configuration for a long time. So now, if I wanted to construct an initial condition off of that information, what would the V out, or the voltage across the capacitor, be exactly at time is equal to 0? So exactly, like right before, the instant before I close this switch at time is equal to 0, what would the voltage across my capacitor be? And hopefully you can see that it would just be 0, right? There would be no voltage difference. If I had completely discharged this capacitor before building this circuit, I would have no voltage difference across my capacitor. My V out at time is equal to 0. Let me even write that in explicitly. My V out at time is equal to 0 is just going to be equal to 0. We are going to have 0 volts, 0 volts across our capacitor at time is equal to 0. So therefore, I can use this initial condition, and it's important to see this initial condition. It wasn't something that I read out of the circuits book, right? I got this initial condition by looking at the original circuit I was given. I was pretty much just given a circuit, given a configuration, told that the switch closes at time is equal to 0. And then I needed to solve for the V output. It wasn't like there was another thing that said, V0 at time is equal to 0 was equal to 0, or was equal to 5 volts, or some other voltage. I needed to figure out this initial condition based on what the circuit was. So now that I've got it, now that I've got the initial condition, let's see if I can use it. Let's see if I can put it into this equation. So now, if I do that, I know that V0, so V0 at time is equal to 0. It's got to be equal to 0. So let me just write down V0, V out, at time is equal to 0, has got to be equal to 0 volts. 0 volts. So we also know that V out at time is equal to 0 is going to be equal to all of this stuff up here at when time is equal to 0. At time is equal to 0. So I'm going to say 0 is equal to Vi plus, let me keep doing it in this color. Vi plus the constant k that we are now trying to solve for, our constant k, times e raised to the minus 0, and 0 I guess doesn't have a minus, so we're just going to say 0 divided by Rc. So now, we've got 0 divided by RC, so 0 divided by RC is just 0, and e raised to the 0, or anything raised to the 0 power, is just going to be 1, right? So now our equation is simplified down. We have got 0 is equal to VI plus 1 times k, plus 1k, so we can even get rid of the 1 there. So 0 is equal to VI plus k. And now for the very last step to solve for k, we know that if we subtract VI from both sides, we know that minus VI is going to be equal to the constant k that we are looking for. So now we have got our final answer for this differential equation. We know now that our, let me choose a good color. Yeah, this is a good color. We now know that our final answer, our V out as a function of time across this capacitor for this first order transient circuit is going to be equal to our particular solution, VI, plus our homogeneous solution, which we have just solved for our K. We know our K is minus VI times E raised to the minus T over RC. And we know that this solution is valid for all time greater than 0. And now the very last thing you can do, if you just want to clean up this equation a little bit, is you can just say that V out as a function of time, we can factor out a VI from this. So we can say VI times 1 minus 1 times e to the minus t over RC. So that is, and for all t greater than 0. So that is pretty much what we've, that is our answer. That's the answer for the output voltage across that capacitor as a function of time. In the next video, we'll start getting into some different configurations, and we're going to see that this configuration that we've solved for right now is really the most important configuration that you're going to have, at least for a circuit with a capacitor in it. And we're going to solve this the same relationship dealing with inductors, and then we're even going to get into second order transient circuits where we have both a capacitor and an inductor in the circuit. So anyway, hopefully you found this useful, and in the next video we're just going to maybe do a few more examples and go a bit more in depth into this. So anyway, thanks for watching, and I'll see you in a future video.